welcome back. So today's subject is digital signal processing. So in that we are going to discuss about the classification of signals. So let us start with the introduction. So signal classification is essential for understanding the nature and behavior of various signals. So it helps in design and implementation of communication systems. This presentation will cover the various classification based on this criteria. So the next is what is signal? A signal is a function that conveys the information about the behavior of a physical system. So signals can be in various forms such as electrical or electromagnetic waves. Understanding signals is crucial in fields like telecommunications, audio processing and control systems. The next is the difference between the continuous versus the discrete signal. So the continuous signals are defined for every instant of time and can take any value, whereas the discrete signals are defined only at a discrete intervals and can represent a sample version of continuous signal. So the choice between the continuous and discrete signals affects processing and analysis techniques. So the next is the difference between analog and the digital signals. When it comes to analog signals, they are continuous in both time and amplitude, resembling real world phenomena, whereas the digital signals are discrete in both time and amplitude, often represented as binary values. So the transition from analog to digital signal has revolutionized many industries. And the next is the difference between periodic and aperiodic signals. Periodic signals repeat at regular intervals and have fundamental frequency. So when it comes to aperiodic signals, they do not exhibit any repeating pattern over time. So understanding the periodicity helps in analysis of signals behavior in systems. So the next is the difference between the deterministic and random signals. So the deterministic signals can be precisely described by mathematical functions, whereas the random signals are inherently unpredictable and can only be analyzed statistically. So this classification is vital in fields like statistics and signal processing. So let's move on to the difference between the energy and the power signals. So when it comes to the energy signals, it has the finite energy and zero average power over time. When it comes to the power signals, have infinite energy but finite power, average power. So this distinction is important for signal analysis in various applications. So the next is the real versus complex signals. Real signal consists of real valued function and are commonly encountered in practice. The complex signals include imaginary components and are often used in advanced signal processing. The complex representation simplifies many mathematical operations and signal analysis. Scalar versus vector signals. The scalar signals have a single value at each point in time, like temperature and voltage, whereas the vector signals consist of multiple values at each instant, such as position in space. The classification is significant in multi-dimensional data applications. The difference between time domain versus frequency domain signals. So when we take these time domain signals, they are analyzed based on their behavior over time. So whereas this frequency domain signals represents the signal frequency components often obtained via Fourier transform. Both representations are crucial for understanding signal characteristics and processing. The next is casual versus non-casual signals. So when it comes to casual signals, depends only on the past and the present values, making them more reliable and real-time systems. So this non-casual signals depends on the future values which are not possible to implement in real time. So this classification is significant for system stability and design. So the next is the difference between the real-time versus non-real-time signals. The real-time signals must be processed as they are received to ensure timely responses, whereas the real-time signals can be processed with some delay and are often used in batch processing. So the choice impacts systems architecture and operational efficiency. Let's see the bandwidth considerations. Bandwidth refers to the range of frequency in a signal occupies and is crucial for communication systems. Higher bandwidth allows for the transmission of more information but requires more resources. Understanding the bandwidth is essential for signal design and filtering. Signal sampling. Sampling involves converting continuous signals into a discrete one of digital processing. The Nyquist theorem states that a signal must be sampled at least twice its highest frequency. Proper sampling is crucial to avoid aliasing and loss of information. At last, the conclusion. Effective classification of signals is essential for various applications across multiple fields. Understanding the different types of signals enables improved design and analysis of the system. Continued exploration of signal classification will drive innovation in technology and communication.